black hole is a region of space where matter has been compressed to such an extent that its gravity becomes unstoppable. Not metaphorically unstoppable, but literally. The speed you would need to escape its gravitational pull exceeds the speed of light. And since nothing in the universe can travel faster than light, nothing can get out. Neither matter, nor radiation, nor information. The point of no return has a name, the event horizon. Cross it and you disappear from the observable universe forever. There is something worth highlighting because our intuition fails here. A black hole is not a hole in the colloquial sense. It is not empty. It is quite the opposite. It is the most extreme concentration of mass that can exist, and that mass warps space-time around it in ways that Einstein's general relativity predicted with extraordinary precision decades before we could verify it observationally. Black holes come in categories. Stellar black holes, the most common, are born when massive stars exhaust their nuclear fuel and collapse under their own weight. If the resulting core exceeds roughly 3 solar masses, the pressure of electrons, and even that of neutrons, is not enough to stop the collapse, and the result is a black hole between 3 and 100 solar masses. Only in the Milky Way, it is estimated that millions of these stellar corpses drift freely. Then there are the giants, supermassive black holes. These monsters lurk in the cores of almost all large galaxies, including our own. They start at 100,000 solar masses and extend to billions. The black hole at the center of the Milky Way, named Sagittarius A star, has roughly 4.3 million times the mass of the Sun. Its event horizon would fit within Mercury's orbit. For a supermassive black hole, it is relatively modest. When these objects exceed 10 billion solar masses, scientists adopt a different term, ultramassive black holes, or, in the most extreme cases, stupendously large. Here arises the obvious question: if a black hole emits no light, if it is by definition black, how do we find it? The answer lies in the chaos it generates around itself. When an active black hole devours surrounding material, that material does not fall straight in. Conservation of angular momentum forces it to form an accretion disk, a flat, rotating structure of gas and dust spiraling slowly inward. Friction within this disk heats the matter to tens of millions of degrees, and at these temperatures it emits radiation of enormous intensity, covering the entire electromagnetic spectrum, from radio waves to gamma rays. These are quasars, the brightest objects in the observable universe. An active quasar can shine with the intensity of hundreds of trillions of suns, visible from the opposite end of the cosmos. Many of these systems also generate astrophysical jets, columns of concentrated plasma shot out from the poles of the black hole at relativistic speeds, extending for thousands or even millions of light years. They are like cosmic lighthouses that radio telescopes can detect at almost incomprehensible distances. For inactive black holes, those that are not eating, the strategy is different. We observe the stars surrounding them. If we see stars orbiting at thousands of kilometers per second around an apparently empty point, something massive and compact must be there. We calculate the mass from stellar dynamics, just as the Sun's mass is deduced by observing how Earth orbits it. It was exactly this method that confirmed the presence of Sagittarius A star at the center of our galaxy. There is another method: gravitational lensing. Einstein predicted that matter curves space-time, and that curvature bends light passing nearby. an extremely massive object acts as a cosmic lens, distorting and magnifying the image of light sources behind it. When we observe perfectly curved arcs of light or full rings around galaxies, we are seeing the signature of titanic masses bending the geometry of the cosmos as they pass. And since 2015, we have a completely new tool, gravitational wave detection. When two black holes merge, the event releases more energy in a fraction of a second than the combined energy of all the stars in the observable universe at that instant. But almost all of that energy comes out in the form of gravitational waves, ripples, in the fabric of space-time that travel at the speed of light. The LIGO detector and its collaborators can capture these disturbances, revealing mergers that occurred billions of years ago. In 2019, the Event Horizon Telescope, a coordinated network of radio telescopes distributed around the planet that effectively turns the entire Earth into a continent-sized telescope, captured the first direct image of a black hole. The shadow of the central black hole of the galaxy M87. It was an orange ring of fire surrounding perfect darkness, coinciding with extraordinary precision with the predictions of general relativity. In 2022, the same team published the image of Sagittarius A star. These are not conventional photographs, but reconstructions from very long baseline interferometry data, yet they represent real information sent to us by the universe and confirm our theoretical understanding. However, we must be honest about the limitations. The farther away a black hole is, the harder it is to measure its mass precisely. For the most extreme objects we are going to explore, measurements are estimates based on indirect models. Some figures have been drastically revised over the years. There are considerable uncertainties, but with that warning in mind, here are the 5 most colossal candidates we have found. Holmberg 15A. The cosmic cannibal. Our journey begins 700 million light-years away in the constellation Cetus. There, at the heart of the Abell 85 galaxy cluster, lies Holmberg 15A, a giant elliptical galaxy that hosts one of the best-studied black holes in this extreme category. Its mass is estimated at roughly 40 billion solar masses. To put this figure in perspective, it is almost 10,000 times more massive than Sagittarius A star, the black hole at the center of our galaxy. Its event horizon extends beyond what Neptune's orbit would be if repeated dozens of times. Light would take days to cross it from side to side. But what is truly fascinating is not its size, but the story that explains it. Holmberg 15A is a cosmic cannibal that has reached this size by devouring galaxies over billions of years. As the brightest galaxy in the cluster, it sits at the gravitational focal point of the system. Surrounding galaxies, irresistibly attracted, spiral inward toward it. And each galaxy that merges brings its own supermassive black hole in its core. When two black holes approach each other, they do not repel or ignore one another. They begin to orbit each other, and that orbit slowly decays as the system emits gravitational waves. Eventually, their event horizons touch and merge into a single, more massive object. This process has repeated dozens, perhaps hundreds of times in Holmberg 15A. Each merger added mass to the central monster in a cosmic snowball effect. Evidence of this violent history is written in the galaxy's morphology. Holmberg 15A has an unusually large diffuse core, a region where stars have been scattered and displaced by the gravitational chaos of multiple black hole collisions. This core depletion is the signature astronomers look for as an indicator of past mergers. It is not speculation, it is the scar left by centuries of cosmic violence. A relevant historical note: early estimates placed Holmberg 15A's mass at 300 billion solar masses or more. Refined measurements in 2019, using more sophisticated stellar dynamical models, reduced that figure to the current 40 billion. It is a reminder of how difficult it is to measure these objects and how our understanding evolves with better data. IC1101, the Galactic Emperor. We now travel 1.1 billion light-years to the Abel 2029 cluster, where we find IC1101, long considered the largest known galaxy in the observable universe. More recent measurements have revised its size downward from the original estimates, but there is no doubt that it remains an absolutely colossal structure, a supergiant elliptical galaxy with a diameter that, in some models, exceeds 6 million light-years. Our Milky Way could fit inside it more than 60 times, and at the center of this galactic empire resides a black hole of roughly 40 billion solar masses, comparable in mass to Holmberg 15A. Its event horizon extends beyond Neptune's orbit, multiplied dozens of times. What sets it apart is not just its size, but its context. It is the black hole of one of the most dominant structures the universe has ever produced. IC1101 has an extraordinarily proportioned central galactic bulge with a radius of about 13,500 light-years. There is a well-established relationship in astronomy between the size of a galaxy's bulge and the mass of its central black hole. The more massive the bulge, the more massive the black hole. IC1101 takes this correlation to its extreme expression. The black hole is not sleeping. It currently produces high-energy radiation jets that propagate outward through the surrounding space. This activity is a direct result of matter crossing the event horizon. Gravitational potential energy is converted into radiation according to the most basic principles of physics. The heat and radiation it emits are so intense that they keep the surrounding gas at temperatures too high to collapse and form new stars, effectively suppressing star formation throughout the central region. IC1101 is an old galaxy. Its stellar population consists mainly of old red and yellow stars. The formation of new stars is practically non-existent. The available gas has been exhausted or is too hot to collapse. IC1101 represents a final state of galactic evolution, a mature system that has consumed and absorbed hundreds of galaxies over billions of years and now, in relative quiet, presides over a graveyard of worlds. The black hole at its center is the testament to this entire accumulated history. S50014 plus 81. The paradox of time. We now enter truly disturbing territory, not just because of the size of the object in question, but also because of when it existed. S50014 plus 81 is one of the most luminous quasars ever discovered and one of the oldest black holes we know. Its estimated mass is around 40 billion solar masses, comparable to previous objects. But what makes this object genuinely baffling is that it formed less than 2 billion years after the Big Bang. Pause for a moment on that number. The universe is 13.8 billion years old, when the light we observe today from S50014 plus 81 began its journey. The cosmos was barely 15% of its current age. The first stars had started to ignite relatively recently. Modern galaxies did not yet exist in their current forms. And yet, there was already a black hole with the mass of 40 billion suns. The problem is not just philosophical, it is mathematical. Black holes grow at a rate limited by what is known as the Eddington limit. There is a maximum luminosity that an accreting object can reach before the radiation pressure overcomes gravity and expels material before it can fall in. If you feed a black hole at this maximum rate continuously, how long would it take to reach 40 billion solar masses? According to our current models, longer than the universe had available. The physical dimensions of S50014 plus 81 are staggering. The estimated diameter of its event horizon reaches about 240 billion kilometers. Its shadow is 40 times larger than Pluto's entire orbit around the Sun, and its brightness as an active quasar was 300 trillion times that of the Sun, roughly 25,000 times brighter than the entire Milky Way. How could it have formed so quickly? Astronomers have proposed several hypotheses. One possibility is direct collapse. Instead of forming a star first and then collapsing into a black hole, an especially massive primordial gas cloud could have collapsed directly into a black hole of thousands or millions of solar masses, completely skipping the stellar phase. This would have given it a huge advantage from the start. Another possibility involves super Eddington accretion at specific periods, something that more recent models are beginning to consider physically plausible under certain conditions. What S50014 plus 81 fundamentally tells us is that our understanding of how black holes grow in the early universe is incomplete. There is something we are not seeing yet, and that scientific discomfort, that tension between what we observe and what we predict, is exactly where knowledge advances. TON 618, at the edge of the possible, we now travel more than 10 billion light-years into the past, to a time when the universe was less than a quarter of its current age. There lies TON 618, a quasar that for years held the title of the most massive black hole ever discovered, with an estimated mass between 60 and 66 billion solar masses. TON 618 contains more mass than the sum of the stars in hundreds of galaxies like our own. The event horizon of TON 618 has a diameter of approximately 390 billion kilometers, 40 times the distance from the Sun to Neptune. A beam of light would take weeks to cross it, and yet, despite being more than 10 billion light-years away, we can detect it because its luminosity is simply unimaginable, 300 trillion times that of the Sun. The story of its discovery is revealing about how science progresses. TON 618 was first observed in 1957 during a photographic survey of the sky. For more than a decade, astronomers thought it was simply a faint blue star in our own galaxy. In 1970, radio data revealed the truth. It was not a nearby star. It was one of the most distant and powerful quasars in the observable universe, and what appeared as an insignificant dot on a photographic plate was actually a cosmic scale event happening when the universe was young. When spectroscopists analyzed the light from TON 618 in detail, they found emission lines broadened by the Doppler motion of matter traveling at more than 7,000 kilometers per second around the black hole. Only an extraordinarily massive object could maintain material orbiting at those speeds. The temperatures and velocities seen in the spectrum could only be produced by a black hole of incomprehensible proportions. Here is an important physical detail. there is a theoretical limit to the maximum size an active black hole can reach. When the accretion disk becomes sufficiently massive, it begins to fragment and form stars. These stars produce radiation that in turn heats and disperses the available gas, cutting off the black hole's fuel supply. This feedback mechanism suggests an approximate ceiling of between 50 and 60 billion solar masses for actively accreting black holes. TON 618 appears to be pushing exactly against that limit. It is as if we are observing an object on the threshold of what physics allows. It is worth noting that initial estimates place TON 618 at up to 66 billion solar masses, but more recent measurements revise it downward to around 40 to 60 billion. Even with these revisions, it remains a uniquely exceptional object, and for years it was the undisputed champion, but not the last. Phoenix A, the last Titan. Our final destination lies 8.5 billion light-years away in the heart of the Phoenix cluster, a structure containing roughly 1,000 galaxies bathed in radiation. At the center of this cosmic metropolis is Phoenix A, the brightest galaxy in the cluster, and within its core resides what may be the most massive black hole in the observable universe, an object with an estimated mass of 100 billion solar masses. 100 billion solar masses. It is 25,100 times more massive than Sagittarius A star, the black hole at the center of our galaxy. Its event horizon extends 590 billion kilometers, equivalent to 3,900 astronomical units. The distance from the Sun to Pluto is 40 astronomical units. Phoenix A's event horizon is nearly 100 times larger than that, and it continues to grow. Phoenix A accumulates roughly 60 solar masses each year, more than a full solar mass every week, added to this object that already surpasses human comprehension. To put it into perspective, while you read these words, while you breathe, while you sleep, Phoenix A has swallowed additional tens of solar masses. This is a process that has been occurring since the universe was young and has not yet ended. How did it reach this size? Scientists believe Phoenix A was forged in the crucible of the early universe, when galactic collisions were far more frequent and primordial, gas was more abundant. Multiple supermassive black holes merged in a series of cataclysmic fusions that fed back on each other for billions of years. In this sense, Phoenix A is not simply a large black hole, it is the cumulative result of dozens or hundreds of merger events, the sum of countless cosmic tragedies condensed into a single point of singularity. Evidence of its violent past is inscribed in the surrounding space. About 100 million years ago, Phoenix A underwent a colossal eruption, one of the most energetic events ever detected in the universe. The outburst carved gigantic cavities in the surrounding hot gas, each hundreds of thousands of light years across, displacing trillions of solar masses of material. These cavities, visible in X-rays, are the scars of an explosion that occurred when dinosaurs still walked the Earth, but whose light only now reaches our telescopes. Time and distance are so vast that observing the cosmos necessarily means observing the past. Here, scientific honesty compels us to be precise. The estimate of 100 billion solar masses for Phoenix A comes from indirect models, not direct measurements of stellar motion in its immediate environment. The object is very far away and extremely difficult to characterize precisely. Some alternative models suggest its actual mass may be closer to 40 billion solar masses, placing it in the same range as the other objects on this list. The uncertainty is real, but even in the conservative scenario, Phoenix A remains an object of extraordinary magnitude, and the nature of the eruptions we have observed in the Phoenix cluster suggests a truly extreme energy source. The balance of evidence for now points to Phoenix A as our primary candidate for the title of the most massive object in the observable universe. We are in a golden era of black hole astronomy, and what we know today is just the beginning. Several projects currently under development or in advanced planning stages will radically transform our ability to study these objects in the coming years. The James Webb Space Telescope, operational since 2022, is already detecting galaxies in the earlier stages of the universe and revealing active black holes at times when the cosmos was just a fraction of its current age. Each new deep observation adds crucial data to the puzzle of how these monsters grew so quickly. Webb's first results have already produced surprises. Galaxies more massive than expected in very early epochs, suggesting that star formation and black hole growth in the early universe proceeded in ways our current models do not fully predict. On Earth, the extremely large telescope, currently under construction in Chile, will have a 39-meter primary mirror, more than 3 times any existing optical telescope. Its angular resolution will allow us to resolve stellar dynamics in the immediate environments of black holes in galaxies more distant than those accessible today, enabling direct mass measurements of objects we can currently characterize only indirectly. In space, LISA, the planned space-based gravitational wave interferometer for the 2030s, will consist of 3 spacecraft separated by millions of kilometers, forming a giant triangle capable of detecting low-frequency gravitational waves produced by the merger of supermassive black holes. While LIGO detects mergers of stellar mass black holes, LISA will be sensitive to collisions of monsters like those we discussed today. Each ultramassive black hole merger will produce a detectable signal months or years before the final event, allowing us to anticipate and study these cosmic catastrophes. There are also efforts to enhance the Event Horizon Telescope by adding more stations in locations such as low Earth orbit, which would dramatically improve resolution and allow us to capture not only static images, but movies of plasma behavior in the immediate vicinity of the event horizon. Watching how that material moves, pulses, and changes in real time would provide direct insight into accretion physics under extreme conditions. The question of whether a black hole exists more massive than Phoenix A, or whether the 100 billion solar masses truly represent the limit of the observable universe, can only be answered with these future instruments. Contemplating these 5 titans is not simply marveling at big numbers. Each of them forces us to ask fundamental questions about how the cosmos works. The first, what limits a black hole's growth? We have seen that there is a feedback mechanism that places an approximate ceiling on the size an active black hole can reach. TON 618, and the others appear to operate near this limit. If the models are correct, we shouldn't find much more massive active black holes, but Phoenix A, if its real mass exceeds 100 billion solar masses, would challenge this prediction. Future observations will be decisive. Second, how do they grow so fast in the early universe? Objects like S50014 plus 81 show that in very early epochs of the cosmos, colossal mass black holes already existed. Conventional accretion-based growth models struggle to explain this. Direct collapse of gas clouds, early mergers of multiple intermediate mass black holes, or super Eddington accretion rates under specific conditions are active hypotheses. This is one of contemporary cosmology's most open problems. Third, how do black holes influence galaxy evolution? We have seen how black holes in IC1101 and the Phoenix cluster emit enough energy to heat surrounding gas and suppress star formation over enormous regions. This feedback between the black hole and its host galaxy appears to be a fundamental regulatory mechanism in cosmic evolution. Black holes not only inhabit galaxies, but in large part shape them. And then there is the question underlying all others: what is inside? Once you cross the event horizon, general relativity predicts that collapse continues with nothing to stop it until a singularity, a point of infinite density where the equations break down. But the equations that fail do not describe reality. They describe the limits of our theory. Quantum physics, which extraordinarily precisely describes subatomic particle behavior, cannot be directly applied to the extreme interior conditions of a black hole using current tools. The merger of general relativity and quantum mechanics into a unified theory of quantum gravity remains the most ambitious theoretical challenge in physics. And black holes are the natural laboratory where this theory will ultimately be required. There is something profoundly human in the act of discovering these monsters. We are beings living on the surface of a medium-sized rock, orbiting a medium-sized star in the outer arm of a medium-sized galaxy. And yet, with telescopes that fit in observatories, with equations that fit on blackboards, with scientific collaboration networks distributed across the planet, we have been able to identify objects 10 billion light-years away whose mass equals tens of billions of suns. Carl Sagan often said, "We are star stuff contemplating itself." There is something equally poetic here. We are atoms forged inside stars that died billions of years ago, organized in configurations complex enough to detect the most extreme limits of gravity in the observable universe. The scale is staggering in both directions. The smallness of our instruments compared to the objects they study, and at the same time the enormity of what those instruments have revealed. That a network of antennas distributed across a planet the size of a cosmic dust mote can photograph the horizon of a black hole 50 million light-years away is, on any reasonable scale, extraordinary. Phoenix A is 8.5 billion light-years away, but it is there, and we know it. This knowledge, in a cosmos so vast and so indifferent, is an achievement worth celebrating. Every time we point a telescope at the night sky, we are not only looking outward, we are looking back in time toward the origin of everything. And in that distant past, these titans awaited us, silent and absolutely immense, guarding the secrets of how the universe built its most extreme architecture. The universe is 13.8 billion years old. It has spent its entire history building these objects, merging galaxies, colliding black holes, accumulating mass in ever denser and more massive points. And we, in the infinitesimal moment we represent in that story, have found a way to see them, to measure them, to understand, at least in part, how they became what they are, and to ask the right questions about what we still do not understand. That is science, and it is, perhaps, the best thing we do as a species.